All right, welcome back. I hope everyone had a great spring break. Today we'll talk about routing, but in the context of the entire internet as opposed to these little routing examples we've been doing so far. Specifically, this is called, internet routing or internet routing, right? Another term for it would be interdomain routing. The idea being that we have a number of independent or autonomous systems, autonomous networks that are managed by different organizations. And their organizations are autonomous in the sense that they make their own decisions bound by whatever contracts they have with other organizations. So, for example, UIC would have their own routing policies. They would have their own rules for which packets are important and which are not, and how they should be forwarding traffic within their network. But when it comes to talking to the rest of the internet, they are told by their various providers, and I would think UIC has at least 2 providers, but probably more. And I really should know that one. When it comes to that, the various providers will tell UIC which parts of the internet are available through them. And then UIC will decide, based on these route announcements, where to send a packet for a certain destination. Generally speaking, you would have at least one provider that offers connectivity to everywhere. And then you might have several other providers that offer more local connectivity, but which perhaps cost less or offer better service or something like that. Okay, so we looked at how to set up routes manually in the past, and I thought I'd just show you, this is from the textbook. Oh, and by the way, we should be reading in the textbook the network layer. Basically, you want to have a good idea of IP, naturally. IP as in the protocol headers, and also the meaning of network prefixes, IP addresses, broadcast, the broadcast address, the net mask, and such. But also you want to have all the basic routing protocols, distance vector and link state routing being sort of the fundamental ways of doing routing, and also forwarding tables, routing, sort of the static routing basics that we've gone through in the past. So this kind of gives a very simple overview of what dynamic routing looks like from an implementation perspective. So the classical network stack, on the physical layer, we have perhaps a cable connecting these 2 machines, these boxes being 2 different machines. And then the data link layer, this might be the hardware on the network card. On the network layer, this is primarily implemented in the kernel of the operating system, and so is the transport layer. And then we have this application layer program called route D. D stands for daemon or daemon, like so many of these little server programs on a Linux computer. So this is a normal application program, or normal program. It receives UDP packets using the standard transport layer, and is able to talk then to a route D somewhere nearby by sending UDP packets. But then after they exchange some messages, they might find out that, oh, I can send packets to a remote destination via this guy. All right, so then it would, route D here would add to the forwarding table, which is managed by the kernel, saying, oh, for this IP prefix, an IP prefix could be, say, a 16-bit prefix, 125.16.0.0, right? For that entire prefix, send all the traffic over to this machine. And this works because these machines are connected via a link layer. Right? They're more or less directly connected. Whereas there might be another link here from this over to somewhere else using a different network, not directly connected to this machine. So now if this machine wants to send to over here, we would have to put something in the forwarding table saying, oh, for that prefix, send it to here first, put something in this forwarding table to say, oh, and then send it on to this next hop. All right, so that's sort of the basics of how forwarding tables are populated by a dynamic routing protocol. So it's normal programs running, and they have sort of limited communication scope. Before they set up the forwarding tables correctly, they can mostly communicate within the network they are directly connected to. But because there's a router that is a computer running this route D, or really any routing protocol you want, right? Within every network, or as long as there is, I should say, at least two, it would have to be at least two routers in every network that speak this protocol. Then you can go from one router to the next, and then as long as these routers are members of more than one network, then they can forward on to the next network and the next network and so on, and they can kind of create a higher layer, a network layer network on top of all these link layer networks. So one way to do this would be to implement, say, link state routing in an application like this, and to say in our previous drawings we had in link state, let's see here we were talking about A, B, C, D, E, right? These kind of abstract identifiers. But we could talk about these identifiers as IP prefixes instead. So we say for IP prefix B, right? This is the route, or there's a link between IP prefix A and IP prefix B. Right? That's a way we could think about it. Right, so we have this implemented. If we build this link state routing in a Linux application, we could then, when we receive any link state updates at one router, perhaps from this invisible other network over here, we can then send it on to this network, broadcast it to all the other routers that are available in this link layer network, and then have all of them also broadcast onward all these link state updates. Right? So in that sense, it's very similar to the more abstract link state protocol view we had in those drawings. And then a big part that wasn't part of that initial discussion was that these routers the applications don't deal with data traffic. They only deal with routing protocol messages. Those are sent to it using a UDP or a TCP connection. But when they've made decisions, they've made routing decisions about a certain subnet destination, they will just add that to the forwarding table. And the kernel will then take on the job of forwarding any packets for that IP prefix subnet without route D being involved. That's quite important. You wouldn't want to calculate the route every time a packet arrives. It is a bit of a job, right? We have to run Dijkstra's algorithm over a potentially quite large network, and packets should really be forwarded as quickly as possible. On modern routers, you could see as much as 100 gigabit per second interface. And to feed that at that rate, you really can't afford to spend more time than a few cycles per packet. Actually, what does it say? We have a 4 gigahertz processor, right? And packets might be, let's see, what's that, 100 gigabit, 100 bits is a little small. Say it's 1,000 bits. Well, very, let's see, what's the smallest packet? 100 bits is a little small. Let's call it 1,000 bits for ease of processing here. So 100 million packets per second, right? That's just to make the math easy. It might be a little faster than that, but let's say 100 million packets per second we need to push out. And we have 4 billion cycles per second. So that suggests 100 million to 4 billion, but 40 cycles, right? We have 40 cycles to make a routing decision. That's a real hurry. Like we don't even have time for on a normal processor, say a cache miss, to read something from RAM. Everything has to be in the cache. Normal routers don't go that fast, but yeah, if they're like a router that needs to be fast, can handle that. Well, it'll be an expensive one. Okay, so that's sort of the general setup. But that's for any routing protocol implementation. The discussion today was supposed to be about this interdomain routing. So why would we not want to have a simple flat routing protocol for the whole internet? Like, we could, in principle, do link state routing for everything. Just one big link state routing protocol. When I disconnect my laptop, a message goes out, and now everyone knows that my laptop is no longer available. And when I connect it somewhere else, a new message shows up telling everyone where my laptop is. In fact, if we did it that way, we wouldn't need IP even. An Ethernet network, which we'll see later on, implements something similar to this. And with a unique MAC address, why have an IP address? We can just send packets to the MAC address and be done with it. That would make life a lot easier, in fact. But the problem is, at least one problem is that that would be a whole lot of messages. So billions of users connecting, disconnecting all the time. There's lots of messages being sent for every little machine appearing and disappearing, and lots of receivers too, right? So say there's a billion of these users. Every time one of these billion users disappears, all the other billion users need to know what happened, or at least their closest router needs to know. We would quickly drown out the network in routing traffic. So one reason to use IP or to use interdomain routing is to try to achieve some better scalability. Right? And there's a couple of ways we do that. One is to associate this IP address with a location, or some sort of proximity within the network, at least. Right? If we share a subnet prefix, there's a good chance, at least if the prefix is long, that we're nearby. Just looking at the IP. If they if they start out looking similar, we can make a reasonable guess that we belong to the same network. Of course, in practice, it's not quite like that, but it's not too far from the truth. That can really help in aggregating routes to many destinations into a single forwarding table entry, and often as a single routing update as well. And that's the other part of it. Not aggregating, but rather hiding changes from the rest of the world. So oftentimes, I don't need to know what's going on in some network on the other side of the world. If I need to reach a host on the other side of the world, I'll send a package first there and let them worry about it at the other end. It doesn't actually impact my routing decisions, so probably I shouldn't be told. So it's not perhaps that it needs to be sort of autonomous organizations for this part, but it needs to be hierarchical in some sense, so that local changes result in local routing updates. Of course, some changes are global. If a big ocean cable gets cut by say an unfortunately dragged anchor or something like that, which happens, then these are big important changes, and there will be lots of routing updates throughout the world. But when an electrician happens to cut the wrong cable at UIC, nobody else needs to know. So okay, so what do we have here? Yeah, first was this sort of aggregation of destinations into subnets, which is part of what IP provides. And I guess if it wasn't for the fact that we wanted interdomain routing, we wouldn't really have IP. We would just use a good link layer. And then there's the hierarchical aspect. And naturally, hierarchy could be done in other ways. I think the distance vector routing, you sort of get that implicitly a little bit, right? Many routing changes don't affect the cost of my cost to a destination. And so therefore there wouldn't be any changes that I observe, and in that sense it's sort of implicitly hierarchical. Sorry about that. Right, where was I? Yes, so there's this implicit hierarchy sort of provided by distance vector routing protocols, where they sort of hide remote updates because they don't really make a difference. With link state routing, you don't get that, at least not implicitly, because all the routing decisions are supposed to be made locally. You need all the routing information. There's an alternative in OSPF, the common link state routing protocol. It's called hierarchical OSPF, where you can divide the network into multiple domains and then sort of shield others from routing updates within your, like, sort of unimportant routing updates within your domain. So there's something there, but it's not something that we see much on the internet. I think that local organizations, larger organizations, probably use it quite a bit. Okay, so those are some benefits, but there's one, and perhaps the most important benefit of interdomain routing is this idea of an autonomous system, where each organization is able to make their own decisions completely within their own network. They have complete control over all routing. It doesn't have to use IP even. It can be anything at all on the inside of their network. And it's only for traffic that goes to and from the rest of the internet, sort of passing the boundary of their autonomous system, that they need to speak IP and they need to speak what's called BGP, the Border Gateway Protocol. So this is the Interdomain Routing Protocol of the internet. If you want to be an internet autonomous system, if you want to join the internet as sort of the, what's it called, a full member or something like that. It's a good term for it, but I forget. You need to speak BGP. A BGP router represents one or more IP subnets. And let's see, an autonomous system. Actually, let's call it like this instead. An autonomous system represents one or more IP subnets. That's the right way. And may have one or more BGP routers. That's the way. Okay. So, so your autonomous system, in fact, let me see if I can find yeah, okay. So here's 3 autonomous systems, AS1, 2, and 3. They each have several BGP routers. The only really important routers in this particular drawing are these 2 and these 2. Inside of the autonomous system, there may be more. I mean, BGP is a handy protocol. You could use it for internal purposes. But basically, we can abstract away all of the routing that goes on inside of this network as just these subnets are reachable from router 2A. Router 2A will send updates to router 1B over a link layer network. Usually it'll be a direct connection. Actually, let me take that back. It'll probably be through a switch, but it'll be pretty direct. So there's some routing protocol messages being exchanged. 1B will forward it to all of the other BGP routers inside of its network. In this case, 1C is the one we're really interested in. Again, using whatever network or routing protocol is available within AS1. And this is not revealed to anyone else outside of the network. They don't need to know even what how we're doing our communication on the inside. And then 1C may or may not forward routing updates from 2A, or from AS2, I should say, to AS3. If AS1 decides to forward a routing update from AS2 to AS3, then AS3 knows of the existence of a path from AS3 through AS1 to AS2, right? And would then install forwarding table entries as any normal routing implementation would do. But if AS1 doesn't forward anything, then AS3 is oblivious of the existence of AS2 on the other side of AS1 and wouldn't add any forwarding table entries. So this is quite different here. AS1 could put in a policy saying, well, I want to be able to talk to AS3 and AS2, but I don't want them to talk through me. This is not something that we've seen in, or that is even possible in link state routing or in distance vector routing, because we have no way to really express it. Like a link either exists or it doesn't exist. This border between autonomous systems is not something you can represent in sort of the standard flat routing protocols. At least not with the options that we've discussed. Okay, and naturally something similar can happen inside, to the extent that the organization wants to have border gateway routing protocol routers on the inside of the network. And usually that's something that would only happen in a much larger network. Generally speaking, you would have BGP routers on the border of your autonomous system. So we could think of this as, assuming there's something more going on back here, this being perhaps AT&T. I don't recall if AT&T is a UIC provider, and I unfortunately don't have internet connectivity right now, so I'm kind of in the blind a little bit. I will upload this video a little bit later when I have connectivity. Right, so let's assume that this is AT&T over here. Actually, I'm going to try to draw this. See what it looks like. Place. Just put AT&T, and then of course the rest of the internet is sort of hiding behind AT&T. AT&T, generally speaking, would be one of those providers that offer connectivity to all of the world. To all of the internet, really. That actually includes AS3, right? So that's a little curious. If we wanted, AS1 could route to AS3 by just sending it to AT&T, and AT&T would forward it. There's some other network here. Let's put let's put Sprint. Sprint is another really large provider of internet services. Comcast is just more of a residential provider. So Sprint definitely also leads to the rest of the internet, and it definitely also has a direct link to AT&T. Prettify this a little bit. Maybe we can even. Okay. Right. And then the AS3 here is connected directly to Sprint. Okay. So now AS1 would receive from AT&T. It receives an update saying, oh yeah, I can reach AS3. It actually doesn't. Well, I guess it actually talks about both the AS and the IP subnet, but we're interested in the IP subnet at the moment. So we can reach the IP addresses within AS3 here from AT&T. AT&T forwards this update, sends this update to AS1. We know about that. Okay, but similarly, AT&T received an update from Sprint saying, oh yeah, one of my customers, I actually have direct connectivity with AS3, this IP subnet. So Sprint would have forwarded a message to AT&T, which was then forwarded to AS1. And AS3 originally sent the message, I have this subnet, sent that to Sprint, Sprint forwarded to AT&T, and AT&T forwarded to us, right? So now we can send it back this way. But AT&T also got it from the rest of the internet. Lots of other people had gotten it from Sprint, and they may have sent it on to AT&T. And we actually received it directly from AS3 as well. So now the question is, how do we decide which direction we should send these packets? Okay, I have to stop here, but I will return a little bit later. See you in a bit. Okay, I'm back. So the question then becomes, how does AS1 decide which route to choose to get to AS3, or the prefixes within AS3? There isn't actually a general rule that applies for this. In normal flat routing, the general rule is let's pick the least cost path. But there isn't a cost. In these paths, there are no costs announced. So in the case of this route here from AS1 through AS2 to Sprint into AS3, AS2 simply says, I have a route to AS3. Well, it says something more. Actually, I forget Sprint's AS number. So we'll just give it a 4. AT&T here will say, I have a route through AS4 to AS3. So the route will look like this, right? Let's see. So some IP prefix, goes through AS2, AS4, AS4, AS3. Something like this is what is announced in BGP. The sort of principle is called a path vector routing, right? So it's similar to distance vector routing, except there's no distance. Instead, we include some sort of abstract path. So in this case, it is a set of autonomous systems. Now, the path can come with lots and lots of attributes, and we'll talk about those a little bit later, but in principle, and I think in practice, at least generally speaking, there are no costs associated with the various ASs. So AT&T doesn't say like, oh, this link is this fast. Sprint doesn't say anything about how fast its links are internally. It doesn't even express any preference about which one, really. And so on. So we have one out here that looks like this. And then we have another one that says AS3, right? So you can easily imagine, right, that this router 3A has announced to 1C that it is connected directly to AS3. And AT&T, as we already discussed, has announced this route. So now how do we choose? This could be a very slow link. This could be very fast. On the other hand, this could be a very cheap link. Right? Maybe it's free. And this could be, well, usually not very expensive, but it could be quite expensive. Or this could be very expensive, right? It could be a satellite link, let's say, a very slow, and also, just in terms of money, very expensive link. So picking this is really not an obvious choice, especially when you're not given the right, like any real cost information. And I think one reason why we're not given any cost information is that users inside of AS1 should not base their decision on the costs incurred at some other network. Right? These are supposed to be autonomous systems. So if there's a cost incurred, it needs to be known within AS1, which means there has to be a contract either on this link or on this link that determines which one they should be choosing. After that, it doesn't matter, right? If this is an expensive link over here, and AT&T is making a loss on this bit of traffic, that's their problem. It's not AS1's problem. I think so. It is sort of isolation of these sort of cost aspects, the contractual aspects of the entire network, the entire internet. Sort of make it so that we really should not be announcing the internal costs. Certainly within Sprint's network, it shouldn't be telling its customers anything about the internals of the network. Sprint wants to say, I offer you flat rate service from here to there at this price, right? Or from here to the entire internet at a fixed price. If customers had some sort of insight into Sprint's internals, they might see that, oh, but you're directly connected to this guy. This should be dirt cheap, right? Whereas this other destination is really far away. Okay, I might be willing to pay some extra for that, or maybe I should go through some other provider for that. These are things that Sprint would like to keep to themselves so that they can make sort of independent business decisions and generally be able to make money. And I should point out that I don't think that that's wrong. I think it is sort of sneaky in a way. But on the other hand, having real profit centers is what makes it possible to expand a network into areas where it's not at the moment profitable, let's say, to invest in new technology and so on. So I generally, I think, support the idea of business playing a significant role in the design of the internet. From a purely technological perspective, I can't say I like BGP. It is quite ugly. But I think it's ugly because business sort of is ugly. Right? Business doesn't have to do with minimizing overheads in a technical sense. It has to do with making money. So, I don't know. It's a difficult discussion. Maybe better to have in person. Okay, so anyway, this sort of gives you some idea of what's happening, but how does AT&T now decide what to announce? Let's see. So this is a good one here. AS3, should it be telling Sprint about AS1? Right? So far we were wondering about how does AS1 decide how to route? Well, okay, so basically it's a business decision. It's been decided internally within AS1 that for all of the prefixes that we are directly connected to by some peer-to-peer link like this, we will use that peer-to-peer link. And you could also add an extra rule, again, strictly internally, say, except for this other one link. Right? This is all, when it's local like this, it's easy. And it's not something that others need to see because they don't, like our forward routing decisions like that are not really impacting anyone else's networks. But now the question is, should AS3 be forwarding the route to AS1 to Sprint? Sprint clearly should be forwarding AS3's route. So here the arrows, maybe I should turn some arrows around. This is not, okay, let me see. That should not be an arrowed link. Let's leave this one like that too. And I'll add, okay. So the arrows here indicate a customer-provider relationship. right. Okay, now that one should also be this. Okay, so this is a somewhat simplified case because both AT&T and Sprint are top-level autonomous systems, core ASs, so they don't have providers. And all of the core autonomous systems, core providers, they're connected to each other, fully connected, I believe. So there are no provider links here. These are peer-to-peer links in the sense that they're both kind of at the same level. All right, but here AS3 is purchasing internet service from Sprint. AS1 is purchasing internet service from AT&T. And these two have a peer-to-peer link between them. So this could be, let's say, UIC and Urbana. Urbana's kind of far away. And we're the same network. Let's call it, no, that's fine. UIC and Urbana. Okay, so now it would be useful to have some sort of general rules about what we announce. There's lots of business decisions involved, and lots of exceptions to the general purpose rules. But still, it would make sense to sort of start with some general rules. One general and very important rule is providers. They announce routes of their customers. Right? So a provider will say, I will route traffic toward this customer. And then, of course, providers also announce all of the rest of the internet to their customers, so the customer has access to the internet. So they are able to send to the internet because Sprint announces lots and lots of internet routes to Urbana in this case. And the internet is able to send traffic to Urbana because Sprint announces Urbana's route to the rest of the internet. Same for UIC here and AT&T, right? But what about this link? So the general rule is that you don't announce peer-to-peer routes, right? The peer-to-peer route to UIC from Urbana is available within Urbana and within UIC, but we don't tell our providers. So AT&T doesn't know that we are connected to Urbana. Sprint doesn't know that we're connected to Urbana. Therefore, they don't announce any routes, so the rest of the internet will not try to send traffic to Urbana to then go over this link, because that hasn't been announced, and vice versa. So for the rest of the internet, it's pretty easy. There was only one route to UIC, we'll pick that one, right? In that case, actually, there's many routes, but there's only one sort of last link. And then there was many routes to choose from potentially within the rest of the internet. Okay, so that's one. And the general, the general rule is you go sort of up. Let's see, we call this sort of core ASs, and then level 1, and then we might have a level 2, so the structure of the internet isn't, it's not this well structured, but let's think of it this way for the moment. Okay, so it might look something like this. Within the core, there's multiple ASs, all fully connected, all advertising routes to each other. And then there might be several little sort of groupings of level 1 ASs that are connected to each other. So, so Comcast and some other, let's see, isn't Time Warner, they have a cable network? Yeah, so for example, the Comcast and Time Warner, they might have links between themselves because they sort of serve the same service area, North America, let's say. But maybe they don't have connections to, they probably don't have connections to all the other level 1 networks, and they perhaps don't have connections to all of the core networks. Right? So they would sort of form a little internet of their own over here, but they purchase service for the rest of the internet from the core. And same thing, so here are UIC and Urbana would be down here. Actually, we're connected, so we'd be in one of these, but there might be other sort of subgroups of level 2, which are purchasing service from some of these level 1 providers. So the general rule is you get to go up. Right? When you route, if you want, you can go up, and you can go across within one route. Sorry, within one level, you can go across over peer links, and then you get to go down. Sorry, let's see, and then you get to go down again to reach your destination. But you don't get to go sort of up. Oh, this is kind of ugly. Up and down and like this, right? You don't get to go up and down and up again and then down. And you don't get to cross multiple peers. You don't get to go from, say, over here through this one, another peer, because these, in practice, it's enforced by not announcing routes. But the general principle is you don't get to go up and then down and then up again, right? This would mean, say, I don't get to go from, in this setting, from UIC. Let's see, do we have a good example? No, we don't, but let me add another arrow here. So Urbana couldn't go to Sprint and then down to us and then up to AT&T, right? They don't get to use our internet link. They have to go up to Sprint and then across to AT&T, because those are both part of the core network. Okay, so BGP is an enormous protocol, and of course also an enormously important protocol with lots of implementations and tons of practitioners. There could probably be multiple classes, entire classes, on just BGP and operation and implementation and all of that. So we can sort of skim a little bit on the surface here, get some rough idea of what's going on. I'll mention a few other details of BGP. I'm certainly no expert in this area, but some things that might be interesting. So BGP deals with prefixes, these IP prefixes. So they're ASs, an originator AS that actually is directly connected to this prefix, sends it to the providers and peers, and they forward it and so on, and they will forward a route per prefix. The longer the prefix, the more fewer IP addresses are sort of part of that prefix naturally. But also the more control you get, right? You could say, oh, for this part of my network, I want this sort of routing. For that part of the network, I want a different sort of routing. So there's some benefit to splitting it into smaller pieces and getting a separate routing entry for each. Of course, there's also some significant cost for that. And the main cost is simply the number of routing entries in the global BGP routing table. The way it generally works, like a BGP router generally is implemented, is you collect this routing information base, RIB, which is all the announced routes that you received from each neighbor. So you get a separate routing information base for each neighbor. You keep that in a little table, let's say, and then applying some sort of prioritization rule, you say, okay, I will use these entries from that neighbor, these entries from this neighbor to collect your local routing information base. And based on that, you will choose your routes for each prefix, and then you put that in the forwarding table of your router. So how many prefixes are we talking about here? How many internet subnets are there? It's not even autonomous systems. There are many autonomous systems, but there's even more subnets, because many ASs, say Netflix, would want to have lots of different prefixes in order to be reachable in different ways from different parts of the world, let's say, or to do load balancing or whatnot. So I pulled up this Wikipedia page. So how many routing prefixes are there? So this is a little bit outdated. That's from 2015. But look at this. Even then, there was more than 512,000 routing entries. So you remember that when I say like route list or just route, in Linux we had 5 or so entries. Here we're talking 500,000, and they keep changing. You have to keep this up to date, and you get these updates from the entire. If you're a proper BGP router, you get all of these entries. You need to see all of these entries. Unfortunately, many of the older BGP routers only had room for 512 entries. 512,000 entries, sorry. So at some point we run into a cap of sorts where we either have to give up on these old routers, or we have to somehow change things to sort of make it work a little bit longer. I think that they managed to get around the 512K limit temporarily, because there was room in those routers for 512,000 IPv4 and 512,000 IPv6 entries. And IPv6 wasn't so popular at the time. There was only some tens of thousands of entries. So they kind of were able to take some of that space temporarily to use for IPv4. So I think that worked out for a little bit, but clearly it's not really a great solution, and many more years have passed since. Hopefully many of those BGP routers were upgraded, replaced, but I think generally there is a really significant scalability problem here with BGP. There's something called route summarization, which has been in place for a while, where routers see that, oh, these two prefixes share all the same route information, and they're adjacent, so I will merge those two into one bit shorter prefix. Things like that to kind of compress it a little bit, but there hasn't been a great solution presented yet, as far as I'm aware. Maybe the solution is just to pile on more resources. Often that works. Okay, another thing that is somewhat interesting is, what if, in this case, now remember I added this, now I have 2 providers. what if I want to say like, oh, I want AT&T to do my routing for Europe, and I want Sprint to do my routing for North America and the rest of the world, let's say. So now anyone in Europe who wants to get to us should get their routes from AT&T. AT&T should be announcing to Europe, but Sprint should not be announcing it to Europe. This is a tricky one, because we don't get to say through a path vector routing protocol, there's no way to really express that, oh, please don't forward this, right? Don't forward this to Europe. It's not like that. You say, I am available, like I have a route to this prefix. That's what you get to say. So there's no way to really tell Sprint where it may forward this stuff to. And thus, Europe would see a route through Sprint and a route through AT&T, and that's no good. So why might we want to use AT&T instead of Sprint? Perhaps there's an agreement about the cost of traffic that crosses the Atlantic. I don't know. There's actually many different reasons why, but let's leave it alone for the moment. Okay, so how can we express this? There's something called communities in BGP. It's a weird term. But basically, Sprint can say, oh, actually, let's not call it, let's think of it as tags. I think tags are somewhat well understood. So you can tag a route with some identifier. In addition to saying, oh, I have this route, I have a route to this prefix, you also get to tag it. So now Sprint can say, oh, for anything that should be announced only to North America, tag it NA, right? North America. Actually, it's a number, I believe, but okay. So now, assuming Sprint kind of sticks to what they say they will do, now UIC can just announce a route to the UIC prefixes tagged with NA to, oh, sorry. It was AT&T, which one was it? I forget. Anyway, let's do, yeah, so Sprint does North America. So we tag it with NA, and we announce a similar one to AT&T, and we tag that with whatever AT&T wants in order to announce only to European destinations. All right, so assuming people sort of have good agreements about what these tags mean and so on, and assuming routes don't accidentally slip out from AT&T through, say, some third core provider, which is also connected to Europe, which then kind of sends the route back to North America, this should work. In general, there are no technical there's no technical enforcement for this built into the protocol. It's just like, oh yeah, you can tag your routes with stuff. But in practice, it usually works out pretty well. Okay, I think we're well over time here. Hopefully you play this back at some higher speed. There was one more thing I wanted to tell you about. Actually, there's a couple of things, but oh well. Yeah, so for load balancing, it's something similar to this North America, Europe thing. I think a good use of this name communities is what we're doing in the Internet 2, which is a bad name, by the way. Internet 2 is not the second internet. It's just a network of academic institutions and some other research institutions. But the Internet 2, anyway, is a sort of peer-to-peer network of lots of largely or maybe exclusively North American academic institutions. UIC is naturally part of that, as is Northwestern, as is University of Chicago, Urbana, and most of the big research universities. So we would announce, naturally, to the Internet 2 that here's us, and would say, oh, but only announce this route to other Internet 2 users. Right? So we don't want to, we don't forward traffic for others through Internet 2. It's just kind of internal to Internet 2. So in that sense, Internet 2 is a community, and I think this is probably where the term came from. I have no idea, I'm speculating here. Another thing that you might want to do with similar things, and I think this is where big time operators like Netflix come into play, is in load balancing. You might have multiple providers to your one data center, but one of the links is getting saturated. Like, oh, my Sprint uplink is getting all the traffic, right? All the incoming traffic. Oh, maybe YouTube is better. They receive lots and lots of uploads. Netflix has an easier time because they can control where they send the traffic. But with YouTube, you have incoming uploads, and you don't get to control incoming traffic directly, but you can by sort of tweaking how you announce your routes. So they could say, oh, let's switch over this IP subnet from AT&T to Sprint to kind of free up some traffic, some bandwidth on the AT&T link to our data center. Of course, this actually requires that you split your IP address range into more subnets so you can announce more prefixes. So you have individual control over each prefix. And that makes the BGP routing table growth worse. So yeah, there's no free lunch. Okay, I think that's it. We'll leave it at that for now. I'm going to do my best to find a stable uplink where I can upload this lecture. And I will see you on Wednesday. Thanks.